Oh, good.
Hello. Okay, thank you very much, Robin. Okay, my name is Daniele Malitesta, and I'm a PhD candidate at Politecnico di Bari. I would like to present the paper entitled Challenging the Myth of Graph Collaborative Filtering. I would like to thank the other authors of this work. Okay, that's a brief outline of what we're going to see in this presentation. And let's get started. As we know, graph collaborative filtering has gained importance over the last few years, and this is thanks to graph convolutional networks which use the message passing operation to aggregate the messages from the neighbor nodes to the ego node, thus distilling the collaborative signal in an efficient way. And that's non-exhaustive timeline of graph collaborative filtering. We start from some shallow GCN-based approaches up to models which use graph attention networks and models which use both self-supervised and contrastive learning, and also and then other methods which try to simplify the message passing formulation by means of some mathematical proxies, and also other approaches which use both the hypergraphs or just explore other latent spaces for the node embeddings. Next slide. Okay. As we know, the reproducibility has become one of the big issues in collaborative filtering, as we can see from all these papers that have been cited in this slide. But in graph collaborative filtering, it's still one of the open challenges. And this is due to the fact that most of the papers tend to copy and paste the previous results for the baselines, or they do not provide the full details of the experimental settings. While we, as researchers, should seek to provide more detailed descriptions of the experimental settings, and also establish some standard metrics for the experimental protocols. So we raised some questions on this. So we want to assess if it is possible to replicate the most important state-of-the-art graph collaborative filtering models, and we just selected 6 of them. Then how they are performing with respect to some classical collaborative filtering approaches, how they are performing on other datasets which are different from the usual ones used for graph collaborative filtering, and then if the information or lack of it coming from the neighbor nodes up to the ego nodes can be impactful on the performance of graph collaborative filtering. So we know that graph collaborative filtering is based on a bipartite and undirected graph, which is built on the user item interaction matrix, which is used then for the adjacency matrix. And these are the 6 selected state-of-the-art graph collaborative filtering approaches. They are from the last 4 or 5 years, and they span some strategies in graph collaborative filtering. We try to encompass most of them. As we can see, all these approaches are not comparing themselves with some strong classical collaborative filtering approaches like the ones that we report here with these citations. And what is more, we can see that none of these approaches is comparing the method with the other graph collaborative filtering approaches. So we refer to the orange ticks, which are reported in the slide. And what is more, all these approaches are only compared, or mainly compared, on 3 datasets, which are the commonly ones used for graph collaborative filtering, but there are then other datasets which are not used, and we would like to also consider them. So apart from NGCF, which trains all the baselines scratch. All the other approaches are taking the baselines and basically copying and pasting the results from the previous papers. Of course, we should know that most of the authors are shared across all these models, and they sometimes use some shared experimental settings for all the models. And so what we have done, we have then included all these approaches in Elliot, a framework for the reproducible evaluation of recommender systems, and then our goal is to provide a fair and repeatable environment for these experiments, and we use the exact same settings of the original papers and codes. Okay, as for RQ1, we use the exact same hyperparameters settings and experiments. So also the same train and test splitting. So the 80 and 20% of the training and test set, and we use then the recall at 20 and the NTCG at 20 as the metrics for this validation. And as we can see from the table, the performance shift is almost in the magnitude of 10 to the -4 or 10 to the -3 for the worst case scenario. So all these models are actually replicable from the papers and from the code that the authors have then provided. Then we decided to add other strong classical corroborative filtering approaches, which are the user KNN, then the ETN KNN, the RP3 beta, and the ESER models, which have been shown to be strong baselines for collaborative filtering. And for these models, we, of course, for the sake of fair comparison, we trained them on the same 820 splitting, but with a validation set and also with a strategy for the searching of the hyperparameters, and it is the TPE strategy with 20 explorations. And as we can see from the slide, these models, so the classical CF1s, are actually equally or even outperforming all the graph collaborative filtering approaches, particularly on the Yelp and the Amazon Book datasets. So we also extended this evaluation to other two datasets. Both book crossing and our recipes, which are not usually used in the graph collaborative filtering literature. As we can see, these two datasets have some discordant topological features and characteristics with respect to the other ones, in particular in terms of the average degree of the user and the item nodes. So, as we can see from this slide, the classical corroborative filtering approaches are actually very competitive and are always outperforming the graph collaborative filtering one. And the only exception is represented by the Ultra GCN and the Leg GCN models, which actually keep their performance as the ones which have been seen in the previous slide. So for the classical datasets where these models are usually trained and tested. And this chart also just confirms what we have been saying. So on the classical datasets, the order is actually chronological, while on the recipes and on the book crossing datasets, the order is kind of reverted, and so that's an interesting point, and we should then look into it. So to further analyze this aspect, we propose a new overview on the information coming from the neighbor nodes to the ego node, and this is called the information flow, and we calculate this with the formulation provided in the slide at 1, 2, and 3 hops. And we calculate, in particular, which is the performance improvement with respect to the average metric, that is the NDCG at 20, and this is the 0% line. And we split all the users into quartiles over the information flow values, which have been calculated again on 1, 2, and 3 hops. And in particular, the best and the most interesting situation is the one for two hops, when we can see that models tend to favor the warm users who enjoyed the popular items over the cold users who enjoyed niche items. And this is especially important and evident on our recipes for most of the models, but on SGL and NGCF. While on book crossing, the trend is almost aligned for all the models. So to conclude, in this work, we tried to replicate the state-of-the-art models for graph collaborative filtering, and we also included other strong classical collaborative filtering approaches, and also other data sets which are not usually used for graph collaborative filtering. And we noticed that the topological characteristics of the user item bipartite and undirected graph in terms of node degree can be impactful on the performance, and especially this happens for the information flow at the second hop, as we saw. For future work, we plan to further investigate these aspects by taking into account the metrics for the diversity and fairness of graph collaborative filtering, and also taking into account other topological graph characteristics, which actually is a work under review and currently on archive. So that's the code for this paper, and these are some QR codes for the paper under review and on archive that I was talking about. So thank you very much for your time.
Thank you, speaker. Thank you. Let's see if we have some questions. I don't see any questions online. Any questions here in the room? I guess one question I have is maybe the title of the paper. It doesn't seem like graph collaborative filtering is a myth. It seems like you're seeing, in some cases these algorithms are working well. So yeah, I guess I'm wondering if that's the right title.
I mean, it's a myth in the sense that in the last few years it has become maybe one of the big deal of the literature, and so we wanted to assess whether it's actually a myth or not. That's mainly the reason why. Then maybe the title was a little bit, funny and different from other titles, but yes, that was the main intention.
The paper kind of makes this claim about sort of structural aspects of the data and how node degree and connectedness basically lead to different kinds of performance. So, I mean, I think maybe a natural question would be to manipulate those features directly instead of going across different data sets. For example, take an existing data set and drop out links and those kinds of things. Manipulate the data to change its graph characteristics.
Well,
try that to see if there's an impact?
Yes, and thank you for the question. It's actually what we did in this last paper that is under review, and it's on archive. So that's a good point.
Okay, so there's a long answer to that question, and read this paper.
Please take a look at the paper in case.
Any other questions? All right, thank you.
Thank you very much.
And